Okay, let's get started. So this is problem number 11 from the Newton second law packet. We've got this pulley system, and we're trying to figure out what the accelerations are, the tensions are, and et cetera, and stuff like that. Okay. So the first thing we need to do here is to analyze this part right here, find this ratio of the tensions. And in order to do that, what we're going to be doing is we're going to be analyzing each of these pulleys, blocks, and the forces that are acting on them. Okay. So let's pick a different color here. Let's use red, I guess. Here's the question. How good are these arrows? Let's try one of these arrows out. Let's see if I can get the arrows to lock to it. Like they're probably going to get stuck, like locking to a specific location. Like that looks okay. So there'd be two forces acting on M1. They would be the tension T1 pointing up, and since we're going to assume that it's going to move downwards, we're going to make the weight a little bit bigger. So those are our two forces. I don't like how here. So the other force is down this way. I guess that looks straight. The values of these forces are going to be, like this one's going to be M1 times G, that's its weight. And then this force is going to be your T1 right here. And then acting on this one, you're going to have if only that last little jitter didn't happen. I love how like just touching the screen does that stuff too. Okay. So shapes, this one, there's a force going up, that's T1. And what if I just copy paste that? Just use my mouse. The mouse seems like way easier to use. Nope. I think the first one's like slightly not straight, so it's doing that. Okay. So there's our two vectors, and then this one right here is going to be ooh, why is it selecting that other pen? Oh well. So this one's going to be your M2G. This is going to be your T2 vector right here. And then if we look at the, how do I scroll up on this thing without using the scroll wheel? I don't know. So now if we look at these, this rope right here, this one rope, it goes all the way from the ceiling down to this pulley and then back to here. And so if the tension in this rope here is T1, and we make the assumption that these pulleys have very little mass, or that their mass just doesn't matter relative to the other masses, we can say that the tension in this rope is the same the whole way. It's going to be T1. So you're basically going to have right here, there's going to be another vector, T1, that's going to show up. Where did my, there it is. There's a vector T, is this because I've got my, the touchpad is like interacting at the same time as the mouse. So then right here, you're going to have this vector T1 that goes down. That same vector T1 is going to be right there. And then on the other side, exactly the same. So this rope is going to have the same T1 right here in both cases. Let's just write that here too, to just be really clear that each of these, oh boy, that's great. Okay, I accidentally pushed the Windows button. So this right here is going to be, oops. This force is going to be T1. And then this force right here is going to be T1. So same thing here. This is going to be upwards. I'm just going to start drawing on here. It takes way too long to switch. This is going to be T1. And then this, oops, let's try to draw kind of straight. This right here, it's also going to be T1. It's a lot of T1s. Oops, 1. But then now when we look at this pulley, can you guys tell me, can anyone tell me, what's the force, what's the tension in this piece of the cable going to be? And if you've already seen this, don't answer too quickly. Yeah, it's 2 times T1, and why would that be? Exactly. Okay, but that's this chord. Did that make sense to everybody? Two T1s here. This has to be T1 and 2T1 as well. It's, yeah, because it's basically like we're assuming we're effectively assuming that the pulley's mass is so incredibly small that it doesn't contribute to the acceleration of the system. Um, which would be like saying, here, let me just go over here and mention what you're saying. So, normally you're saying, is it like equilibrium, right? Okay, so normally with equilibrium, we'd say net force is equal to 0. But here now we're talking about Newton's second law, where net force is equal to mass times acceleration. But if we say that the mass is really small, right? If this is negligible, then the whole thing becomes 0. Yeah. Yeah, it is accelerating, and what we really need to do to be 100% accurate in this problem, we'd also have to include in this the masses of the pulleys, but then the problem would get even harder than it already is, so we're not doing that right now. That's, if you ever wonder why we do these problems in physics, where we say, oh, we're just going to neglect this and that, it's because we don't want you to have to solve a system of, in this case, I think it would be 10 equations with 10 unknowns, and that just wouldn't be fun, I don't think. Okay, so the next thing we would do then is say this force is T2, sorry, 2T1, double the tension T1. So now we say, okay, right here, then you also have this force going upwards, and that one's going to be 2T1 as well. Getting kind of cramped in here. And then on the other side, the force up here would be 2T1 as well. So you can see the pattern, which means on this one, the force down here, that one's going to be 4T1, right? And then on this pulley, you've got going up, you've got 4T1. And then right here, you've got 4T1. Which means on this side, what's this one going to be? And so now we can, no, it's okay. So now what we can see then is that the tension 2 right here has to be equal to this. So that gives us our relationship. So for part A then, basically that's our answer, is that T2 is equal to 8T1. That is the answer, at least part of this. And one of the equations we're going to need to use later on to solve for the acceleration. Does that make sense to everyone? Does anyone have any questions? Okay. Look at all this mess you have to do to describe what's happening here. I probably could have just pointed and stuff, but it's kind of necessary. Color coding what? I tried to make all the vectors the same color. Is that what you meant? Or I could probably use different colors for each. Like T1 could have been blue, and then T2 could have been something else, but they're all ratios of T1s. I don't know. You're probably right. Okay, so the next thing we need to do is to figure out this part, what the ratio of the accelerations is here, right? And can you guys see the mouse cursor? I don't think you can. So I have to do this. If you you can, I know for a fact it's not recording it in OBS, so people on YouTube wouldn't be able to see it. So this is the thing we're gonna look at now, how we do this. And for this, we kind of need to draw a new picture over here. And what we're gonna do is we're just gonna look at our first pulley system and use that as a way to describe what's happening. So I almost wish I had just copied this over here. Darn. Shouldn't be too hard to replicate it though, because I'm gonna have to redraw it again anyway. So can I save this and then undo until I only have that part and then reload it? I probably can, right? This is savable? Gotcha. Yep, that's what I was thinking. Let's see. View, insert. Oh, just like Control A, copy, and yeah, the book, quick notes and title page, search this thing. Like here. I just made another page, yeah. Okay, it automatically did it, so it's fine. Yeah, so now we can do it, right? Nope. Wait, from here. That's working. Nope. We've. Yeah, I know. All right, whatever. Okay, we'll just draw a new picture. This is really great quality content for YouTube. People are gonna love it. Okay, so let's see. Close this. All right. We'll redraw this now. This is gonna take a while. So now we need to draw another one of basically this piece here. I'm probably just gonna try to lasso it and then do some erasing. That's probably the best thing to do. So draw, lasso, click, lasso. That's the piece we want to cut out. I didn't get the bar at the top. That's fine though. Okay, we'll put it like right here. So there's our pulley system. You can always do a new line across this top. I guess it's fine that it's that color, but if we make it black, shapes this one. Okay, so there's our system. And now I just want to kind of erase some of these things. Okay, we're calling the acceleration of this block right here. I just noticed that it took everything away here just now. Good thing it's, oh, but it's gonna do that, really? If I paste, it's gonna take the whole thing back? Okay, so we're gonna have to copy this one. I can't do that though, can I? Because it's gonna erase it on the clipboard. If I do that, it's going to erase the thing that's already on the clipboard, which is this. Like, when I copy to clipboard, it's doing that. That's paste. It's not undo, it's paste. Why would it move it back? That's a really interesting feature. I don't know that I understand that at all. I don't think we need this that much anymore though. So we're just gonna work over here and deal with what we can. I could do this, copy paste. I thought that's what I had done before, but it is what it is. Okay, there we go. All right, so now what we need to do is consider what happens when we move this object down by some distance. And the distance that we're going to move it down by is exactly the distance to move this one up to here. Okay, so we're going to move this one down by a distance, and we're going to see what happens when we move this piece right up to here. Okay, so we're going to make another little section over here. How do I go to the right? And it's not showing up because that one, this one. Okay, so we're going to draw another little section of this right here, but just imagining what happens if it moves up. So we'll take the circle, and we're going to move it on the same level right here as this pulley, and then we'll just copy paste that one and put it right next to it. So there's our two pulleys. They're going to be basically adjacent to each other at this point. And then we're going to run our rope through this. I can't believe I'm just using my mouse for all this stuff. Seems just about as easy. Okay, so the rope goes here now, around here, and then back through here, and then back down to here now. The question is, like, where is that mass going to be? Okay, so this mass will have obviously have gone down by some distance, and we need to figure out exactly how far it's going to go. Okay, and so I'm going to draw exactly how far it goes. So it's going to be, let's see, it's basically going to be this plus this. So this length here is going to be something like about this far. writing is not as easy with the mouse, but whatever. Does that look right to me? Or is that too far? It should be this one. This one. I've gone too far. I'll shorten it if I need to. It's easy to do. Okay, so what happens here now is that this, I'll start writing now because it's easier to do the rest of this with pen. Oh, whoops. We need one more line here. This guy is still connected to the ceiling. Okay. So the distance that this pulley has gone upwards is, we'll call this distance d, or let's call it y. So this pulley has moved up a distance since its center of mass was here and it's now here. It's moved up a distance that we can call y. And you might notice that the distance between here and here is also y. It's the same distance basically, right? So now that the pulley has moved up, then what's going to happen is that mass 1, which was originally at this level, right? So let's just put a little dash line right here. This was the original level of mass 1. So mass 1 has moved down this far. Now, is it just because I drew it that way, or is there some reason to it? So what I would argue is that this distance that mass 1 moves is now 2y. And I'll try to argue as to why that's the case. So if this mass moves downwards by any distance at all, it has to lengthen the string between this point and this point right here. Does that make sense to you guys? This string has to get longer. Does everyone understand that? Like that if this mass moves down to here, the string clearly has to get longer. But it's string, right? And string can't just come from anywhere. You have a fixed amount of string that you can work with, right? And this is how much you have to work with. Just that much, right? That's how much string you have. So any string that comes, and now I need to use the mouse to show what I'm saying. The string, right, that you need to pull to get extra string here, it has to come from here. Just for people on YouTube. So in order for that to happen, you need to pull string from between these 2 points and from between these 2 points. And that's why you have to have you get twice as much string here as you do from these two. So that this pulley, it moved up a distance y, while M1 moved down a distance that's 2y. Do you guys have any questions? That was a really bad explanation, but it's just the best I could do impromptu with the tools I have available. So please ask questions, and I'll probably have to explain it again. That was completely, like, you guys understood that, or no questions at all? Do I need to check the chat? Let me check the chat. I see someone typing. Maybe they have a question. It's okay. Don't be shy. This is really complicated. I want to help you guys. So no questions at all? You guys understand why if this one goes down 2y, that the pulley itself right here only goes up y? Does it make sense? Okay. So once we know that, we can say the following. Um, if I take this, right, 2y, and say that that represents the y coordinate as a function of time for this mass, right? Then I can take the time derivative, right? And I can say, okay, well now I know that the velocity as a function of time would be basically just, well, equal to 2 times dy dt, right? Which should just be v, vy you might call it, or something like that, right? And then you say, well, what's acceleration? Well, acceleration is you take the derivative of that. So the acceleration as a function of time is going to be equal to, 2 times just what we would call a. In this case, that a happens to be a1. This is a confusing way to explain it, I now realize, because this is confusing. What I want to say basically is that the acceleration of the pulley needs to be half the acceleration of this guy. And I can do that, but sorry, someone's talking. What's up? All right. So that is, let me just call out who that is real quick. Oh, they fixed it. Cool. All right. So this is probably a confusing way to explain this. What I was trying to say though is then if you have an object that starts at y, then its velocity is going to be v and its acceleration is going to be just a. If that makes sense. This is a horrible way to explain this though, as I realize as I say this. But the point is that what you get from this is that the acceleration of the pulley ends up being half of the acceleration of the mass. That's the main thing I wanted to like pull out from this, is that the acceleration of the pulley is half the acceleration of the mass, m1. Right? So does that make sense to you guys? If it moves a certain distance in a given amount of time, then you can turn that into velocity and you can turn it into acceleration. Okay, so let's work through this then. Maybe you guys want to try to work it out for yourself. If I now know that if this is A1, that now this pulley here, can anyone tell me what would its acceleration be relative to A1? Yes, so this is going to be A1 over 2. And then we replicate the system again, right? Because this pulley here, if it goes up some distance, right, it has to pull string between here and here. And it's going to have to pull string from both of these sides. So can anyone tell me what's the acceleration of this pulley going to be upwards? Yep, so this one's going to be A1 over 4. Kind of running out of space here. And then how fast is this one going to move then? This one's going to go up at, yeah, and so I'm just going to write down here that basically this one, yeah, we'll put A1 over 8. And that means that A2 is equal to A1 divided by 8. Now we have the answer to part A. T2 is equal to 8T1 and A2 is equal to A1 over 8. And if you think about this, that means that there's another way you can think about this that someone mentioned. If you know that M1, when it moves down, if you know that it moves down by some distance, and we call it, you know, X, right? You could say that any work you do in pulling it down, you'd say that the work would be the force times X. And we haven't talked about work yet, but a prerequisite for this course is that you've taken like some kind of physics before, so you probably know about work. And the way that these mechanical systems operate is that any work that you put into them, you can never get as much work out of them. And the maximum efficiency of a system like this, which would be 100%, which would say that any work you put in, you get the same amount of work out of the system. Does that make sense? The pulleys produce something that I think is often referred to as mechanical advantage, which is that because of this relationship here, the T2 equal to 8T1, it means that basically the mass of this object, okay, gets communicated 8 times down here, right? Because whatever tension you need to support the weight here, you get 8 times the tension right here. Does that make sense? So if this was a 1 kilogram mass and this was an 8 kilogram mass, the system would actually be in equilibrium. We'll prove that later on. So 1 kilogram could support 8 kilograms, right? You can expand this even farther. Let's say that you want to put a 10-pound block here. You could lift an 80-pound block here. You can go even farther. You can say, what if you want to lift a car? Well, if a car weighs, like, let's say 1,000 kilograms, then you only need an eighth of that here in terms of force to actually lift it up. Does that make sense to you guys? What's 1,000 divided by 8? Can you guys lift that much weight? Let's see. Probably wouldn't be that hard. 1,000 divided by 8 is like 125, right? Yeah, 125. 125 kilograms is probably, it's a lot of mass. It's the mass of a very heavy person, but I think hopefully you guys get the idea. The point is that if I want to put a small amount of weight on here and lift an object here, then this object, I'm going to have to pull it farther to get this one to go up. Does that make sense to you guys? You're going to have to pull this one farther, so you're going to have to do the same amount of work to pull it down as the work that's done on this object to make it go up. And that's why this one would only move, well, 1/8 as far, or have 1/8 the acceleration of this object here. feel like I over-explained that to death. Not at all. Okay, so what we say is that you've got a rope here, right? And that rope, if I take this rope and I pull this object downwards, I need to increase the length of the rope between these 2 points. So that means that I got to pull rope from somewhere. The only places I can pull rope from are basically between these 2 points here. So like from here and from here. Let me highlight in green which pieces of rope you can actually pull from. Just do like a really thin green line here. So basically, these are the only rope lengths that you have to work with. Oh, I love when it does that. I love when it switches back to the ink one. Okay. So basically, you have this length of rope here, and you have this length of rope here. That's the only place you can pull rope from. I don't know if you guys can tell why, but um, well, maybe this length can change. Certainly, I think that basically the length between here and here is fixed. The length around the circles is fixed as well. So you're basically only pulling lengths of rope from the 2 green spots right here. And so when you pull rope from there, you have to pull equal amounts on both sides. So that's why you have to pull Y here, and then that moves 2Y. Does that make sense? Whoever asked that question? You can find other demonstrations of what I just described online if you want other people trying to explain double pulley systems, maybe more clear than what I did, but that's the whole point of interacting with you guys in Discord is I can get real-time contact. Like, you guys can tell me what you think immediately, so I don't have to wonder what you're thinking. It makes it a little more like an interactive class and stuff like that. Okay, so we got these, and now we want to find acceleration. That's the last piece of this problem, right? So let's start working on that. We'll need these 2 equations, of course, but really the only other thing we need is just some free body diagrams. We already have the free body diagrams, actually, don't we? So we've got this one, right? Let's go ahead and start writing down our equations. In fact, maybe can I keep these both on the? Yeah, I can keep both these on the screen. So the only force that's missing from here is the force that I erased earlier. So let's draw back in. That was the force. Oops, that's the wrong end of the pin. I don't want to do that. That one, the T1. Okay, so let's write our equations for each of these objects. So for M2, we're going to have, let's use black for the, or let's use blue. So for M2, we're going to say that the net force acting in the y direction should be equal to the mass of M2 multiplied by its acceleration, which is A2. And one of the things we have to do for problems like this is we need to make the direction of the acceleration be positive. So we're going to make the coordinate system here be such that this is what we're going to call positive y. Because again, you make the direction of your acceleration positive. That's a really important thing about these type of problems. So if we make up positive, then that means we need to make T2 the positive vector here. So we'll say T2 minus M2G is equal to M2 multiplied by A2. Hope that makes sense to you guys. And then we're going to do M1 over here. So for M1, which direction do I make positive for this guy? Up or down? Okay, so we make down positive. We say net force acting in, we'll call it the y direction, is equal to M1 times A1. And then we're just going to say we've got M1G minus T1 is equal to M1A1. And then we can start working with these equations. Writing on the bottom of the tablet's kind of awkward. Oh, and we need to use our other 2 equations here, so we'll leave those on the screen too. So T2 is equal to 8T1, and we need this one too. A2 is equal to 8 1 over 8. Okay, so next thing is here, we need to eliminate one of our variables here. It doesn't really matter which one we do. We can start off by saying T2 is equal to 8T1. Let's put that one in here. So we'll have 8T1 minus. And the next thing would be to replace A2. Yeah, I think it's okay to replace, I can't remember if it's neater if you replace this one, or if I replace this one, this will become 8A2. I think that's what I want to do. So we're going to leave this one as M2A2. This is just to avoid fractions in the final answer. And over here, we're going to replace the A1 vector. So now it's going to be 8. So it's going to be M1 times 8 times A2. And now we have the ability to eliminate our T1 vector from here, or we can substitute, we can solve for T1. So we can say M1G minus 8 M1 times A2. I just subtracted that one over, is equal to T1. And then we can plug this in right here, right? So we can take this whole thing and we can plug it in basically right here. So we'll have, just scroll down just a little bit on this side. So I guess I can, basically each one of these can be a different thickness, can't it? So I can have quick access, is that the idea? And I can add extra pins here. Okay, I need to play with that more. Is there a question, or is that just is that background noise? All right, so we put in here, we say 8 times M1G minus 8 times M1A2. Maybe I should have had you guys solve all of this out for yourself at the end. But we're like one line away, so we'll just finish this and we'll take a break. So we're solving for A2, right? So we got to distribute through here. So 8. Please yell at me if I make a mistake. So 8 times 8 is 64. Solving for this, getting all the A2s on the same side of the equation, what we're going to get is 8 M1 minus M2. All of that's times gravity. That's this term and this term. And then all of that's going to be equal to, it's going to be A2 multiplied by, this is A2 times M2 here. And then we add this term to the left side, the right side, so plus 64 M1. You can go through the algebra yourself if you want to see. I skipped like maybe one step here. Maybe more depending on how you do it. And then, yeah, we get an answer. And what I could do actually is probably just erase this and put it over here, but we'll rewrite it so we can write it large. So our final answer is 8 times M1 minus M2, all of that times gravity. And then we divide that by M2 plus 64 M1, and that's going to be equal to A2. And you can figure out what A1 is by saying that if you multiply A2 times 8. Just one second, that last line there was, I don't want to, so there's our answer. We're going to look at some specific values of this, but do you guys have any questions? Did I do my algebra right? Okay, what's the answer to this? So if I make M1 equal to 1 kilogram and M2 equal to 8 kilograms, what's the acceleration going to be? Right? This probably should go with a darker pen here, to be honest. And so then, so what if we pick some values like, we know that it's 0 here, right? And so do you notice how it comes out in the final equation? Let's talk about what this equation says. It says that whatever mass M1 is, right, 8 times that, I need to do this with the mouse, 8 times mass 1 minus mass 2 times gravity. That's the biggest factor in determining what's going to happen, right? So mass 1 contributes 8 times as much to what happens in the situation. Does that make sense? That's why M2 can be 8 kilograms, M1 can be 1 kilogram. If we go back and look at that, if this was 1 and this was 8, the system would be balanced completely, just because of the way the pulleys work, right? Each one of those pulleys basically, increasing how much weight that this little thing can support by a factor of 2, right? So 1, 2, 3 pulleys, you get a factor of force amplification of 2 times 2 times 2, right? If we put another pulley in here, it'd be 16. Put another pulley in here, it'd be what, 32? Yeah, 32, right? It's kind of the power of what these pulleys can do for you. Yeah. If we chose different values here, for example, if we made M2 to be slightly larger than this, what would happen to this right here? Like, what if you make M2 to be equal to 9 kilograms? What happens to this numerator right here? What does it become? It'd be negative, right? So our original assumption was that A2 was moving upwards, right? But if the values get changed, then our answer will fix itself and it'll say, oh no, actually A2 is going to go down now because now if this is 9 kilograms, then it's big enough mass that it's going to have more force downwards here than the tension being provided by the weight up here. Did that make sense to you guys? Did I go through that too fast? Okay. We can also calculate a value here, and maybe we'll do that after I stop the recording. So I'm going to stop the recording here as we've gotten to the final answer.